in teaching fractals, I usually start with a motivational activity. Okay? I'll ask them to draw the picture that fits the sequence of images. Okay? So I have the first picture, which I call the base. The second picture, my motive. And then the third picture, what do you think will be the fourth image after the third? So I'll give you 5 seconds to internalize the problem and perhaps visualize the fourth image. Okay, 5 seconds up. So what you observe in the third image, it actually substitute the second image to the first image. So that's the substitute the second image to every line you see. So basically, you substitute the second image to the first image, which is a line. Okay. So for the second image, you substitute again second image. So for every line you substitute the second image, you arrive at the third image. Clear? Is it okay? Okay. Now, for the third image, try to substitute again the second image to every line. So you arrive at this. Okay? So one will observe that if we keep bending the lines get longer and longer. Would you agree with me? It gets longer, right? You have more lines, it gets longer if you straighten it up. From the naked eyes, it looks like it looks finite because it's there. But mathematically speaking, it is infinite because you keep bending it. Okay? Like the animation shown at the top. Okay, keep bending it so it's actually infinite. Okay, second, this will be easier because we now know the patterns. So, given the first, second, third, okay, you'll come up with something like this. Okay, and if you look at it, it's a very nice picture. It looks like a tree. So, if you need some oxygen in your room, perhaps you can draw a tree and then post it there, and then you can feel that there is better oxygen in your room. Okay? And then I'll ask them to do another one. And usually after the first one, they already grasp a feeling of how to create their own fractals. And then I'll ask them to observe, okay, what they notice and how they create the fractals. So a while ago I told you the solution, but actually they have to tell me how they form the fractals. Okay? They have to share it to me and then I will summarize it for them. But earlier, I summarized it for you. Okay? So, the father of fractals. Okay? It actually started with Gaston Julia. This is for algebraic fractals. Okay? So, in around 1920s, Julia actually published his paper about on the iteration of a rational function. Okay? Rational function. And he became famous for it. However, after his death, he was also forgotten, like many other scientists. Okay? However, it was in 1970s that the work of Gaston Julia was revived and popularized by Polish-born Benoit Mandelbrot. Okay? Inspired by Julia's work and with the aid of computer graphics. Okay? Mandelbrot actually worked in IBM. So he used his resources to actually study Julia's work. And the first picture he created out of Julia's work is a beautiful fractals known as Mandelbrot set. Okay. So if you look at Julia, you will notice that there's something in his nose. I think now you're wondering why is there something in his nose. Okay, it's not a costume party that he has to put a mask in his nose. He actually lost his nose during World War I. So this will be a summary that I will take from my students. So for fractals, you will observe that you can actually shrink it and apply zoom in multiple times, an infinite number of times, and it will still look the same. Okay? So it also involves symmetry of magnification. Symmetry is a topic that will be discussed in some other modules. So what are the main properties of fractals? Okay, I'll tell them that, okay, it's you have self-similarity. So what is self-similarity? If you look at Sierpinski's triangle, it's outlined in an equilateral triangle, the first one. Okay. If you look inside, all the triangles inside are also equilateral, the last figures. So all the triangles there are equilateral. If you zoom in and zoom in, you'll always find equilateral triangles. And then it also, for fractals, it's also in both dimension. Actually, there's some confusion in defining dimension, because what the dimension that we know is the first dimension, which is usually a line, right? Then for second dimension, it can be represented by a square, right, for plane. And then we have 3 dimension. But for fractals, it's different. They define their dimension, it can be in between 1 and 2. So it can be 1, like for this one, it's 2.4 for the Sierpinski triangle. Okay, it can also be between 2 and 3. Okay, instead of stating it as a fractional dimension, actually Mandelbrot called it roughness. Okay, he defined it as roughness instead. So if you look at the Sierpinski triangle, on the second triangle, we made the length of twice as small as the first triangle. And then after doing this, the second triangle will see 3 black triangles, right? The second triangle, the second illustration. Okay, based from the formula in calculating the dimensionality of fractal set, it's the log or ln of number of pieces. So for the second illustration, how many pieces of black equilateral triangle did you see now? 3. Okay, so it's log of 3. And then the multiplication factor is 2. Okay, because you divide each line, each sides of the line into 2, and then you cut them. Okay, so log 3 divided by log 2, that's actually equivalent to 1.58. Okay, this implies that the Sierpinski triangle take up more space than one-dimensional number line, but takes up less space than two-dimensional number plane. So there's actually a hunt, but there's a question whether stating the dimension as non-integer, what does it imply? How can we let our students appreciate it? Because you can see first dimension, second dimension, third dimension, but how about 1.5 dimension? How are we going to let them appreciate what is 1.5 in terms of dimension? And to understand this, I have to mention the term roughness introduced by Mandelbrot, because it is not possible, like in geometry, to measure the perimeter or area of fractals. Okay. It's difficult to measure the perimeter or area. However, in able to define roughness, there need to be some rethinking about the concepts of dimension in math. So, I think I have enough time. So let's see how we can arrive at a formula to define dimension. Let's first focus on the first dimension, which is a line. Okay. So for the line, R is defined as the scaling number, okay, meaning how many times I divide it, or 1 over R is the magnification factor we had earlier, okay, and N is the number of pieces you will observe after we cut it. So before cutting, we have, it's a 1, okay? It's a 1, it's not a 7. It's, okay, let me erase it. Okay, now, next, I'll cut it into half. After I cut it into half, my R will be 1/2. Okay? And how many lines I observed after cutting? 2. Now, I cut it then again. Okay? 2/4. And then how many lines do you observe? 4. So if I follow this order, I will actually get you agree? If I find the reciprocal of R, it will actually be equivalent to N. agree? Okay. I'll erase it. Remember that 1 over r raised to 1 is equivalent to n. Next, let's move on to the second dimension. Again, for the first r without cutting, we have 1, and n number of squares we have is also 1. Now I cut, for every size, I cut it in, divided into 2, into half. So I cut it here, 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 here. Okay, I cut it. Okay, so my r is 1/2, and my n, how many squares? Now I cut it further. Basically, our r is 1/4, and our n is, and if we check the formula, this is can be arrived as 1 over r squared equals n. Okay, if you notice the exponent there actually can be associated to the dimension. Okay, the first is first dimension, and then for plane we have the second dimension. Okay. Now let's move on to fractals. Okay. Given the illustration earlier, so we have 1, 1 without cutting. Okay. The second illustration, okay, is actually cut by thirds. Okay. You divide it into thirds, 3 parts. This is 1 part, second part, third part. Do you agree? Okay. So cutting into thirds, how many lines or how many patterns of the same did you observe? So this is 1, 2, 3, 4. Okay? Now you cut them into 9 parts. How many lines? Or this is just a summary actually. So how many same patterns did you observe? It's actually, again, 16. Okay? We follow the formula that we have earlier. And we want to calculate D. Okay? So how can we solve for D? We apply log, right? So this will be D is equivalent to log of n all over log of 1 over r. Okay? In particular, if we solve for log of n, 16 divided by log of 1 over r, or log of 9, will arrive at 2.16. So the dimension for this fractal is 2.16. Okay? So that's how we arrive at the formula that we showed earlier in relation to the dimensionality of fractals. So now we move on to applications. Okay? So fractals are actually everywhere. Okay? It looks like a tree that I captured somewhere, but no, it's actually a tree that I generated through drawing or simulations. So we find patterns in tree. Okay, it actually shows the successive stage of growth closely resemble to the earlier stage on the left side. Okay, so there's actually a very interesting research that I come across with. So it's about how they are actually measuring the carbon dioxide fluxes of a tree in a forest. So instead of measuring every tree, the carbon dioxide fluxes of every tree, what they do is, from the concept of fractals, they know that there's a pattern in how the trees grow. So they just need to measure one tree, measure the corresponding carbon dioxide fluxes, and then can generalize that, okay, in this forest, okay, the carbon dioxide flux absorbed in this forest is this. Okay, and then they can give that as a report to any environmental association or group, and then it can give them suggestion whether they need to plant more trees or they can cut more trees. Of course, we don't encourage them to cut more trees. Okay? So it can also be found, okay, in our human body. Okay? This is actually our lungs. Okay. Next, this image of, actually is an example of roughness fractal growth found in colonies of bacteria, in particular Bacillus subtilis. Okay. Varying branches are caused by changing of the environment conditions for the bacteria as they grow. So you can see that on the right side, these are simulations. Okay. And on the left side is that an actual image from the wet lab. You can see the resemblance of the growth of the colony of the bacteria. It's really amazing. How about in engineering? So I'll give you an example. They call it the fractal antenna. Okay, it's the antenna. Okay, they uses the Minkowski fractal. Okay. They actually suggest that self-similarity was one of the requirements in able to make antenna frequency and bandwidth invariant. In other words, self-similarity aspect was the underlying requirement along with the origin symmetry for frequent independence. Okay, maybe you can also ask the engineering students to think of some other products or some other innovative idea where they can also apply fractals. Who knows, the solar panel can also be created using fractals. Who knows? Okay, and then there's a paper in business, how fractals is applied in analyzing business cases. Actually, when Mandelbrot started, the motivation was a series of financial data and simulation he got from his work. And when he tried to analyze the data, that's the time he got into fractals. Okay. So it does have some applications in fractals. I think this is also a good platform where you can have your research for interdisciplinary research, because you're math majors, and then you can also do interdisciplinary work with businesses and applying fractals in analyzing their business problems. Of course, in nature, we have the zoom-in illustration of the leaves, and then on the right side, it's actually the river network of the Amazon. Okay. So it's very interesting how God created the world, because He actually have a lot of things there, but everything has its own patterns, and there is informing those things. We have the flowers, have the leaves, and on the other side is have the snowflakes. Okay, in art, so this is now the digital art. Okay, so for me, I'm not good in drawing. I'm really poor in drawing. So, but this is a good news to me because I don't need to draw. I just need to type my equations and plug in the color that I wanted. And I can also be an artist, and I can also perhaps have my own exhibit someday. Okay. Still in art, so we still go back to Hakusai-san's paintings. It does not only include spiral ratio, okay, or golden spiral. It actually also includes fractals. If you look at the waves, at the end of the wave, edge of the waves, there are fractals there. Okay. Same in the clouds, formation of clouds, these are fractals. In the earlier year, actually very few people appreciate Hakusai-san's painting. It looks animated. But once they see that there's fractals there, more and more people appreciated his work. And it's now very expensive. Okay. Also in architecture, you all can also see fractals. In fashion, okay, I was supposed to wear a t-shirt with fractals, but I ran out of time, so I just wear a plain white shirt. Okay. And then also in movies, okay. So the computer graphic using fractals was first applied in the movie Star Trek 2. I don't know if I'm already born, but maybe. Okay, so they use actually fractals to create the textural landscape you see on the slides. Okay, and now they improve it a lot, and you can see a lot of special effects in Hollywood and even in TV or advertisement. Okay, I'm supposed to show a video. I don't know if this will work. This is actually a video how they created the mountings in the video. Okay, so I have last 2 minutes. So the concept there is very simple. Let me find my mouse. I can't find my mouse. Okay. Okay, it's not working. It's supposed to be a video. It's showing you how they created the mountain. So it's the concept there is very simple. They draw 2 huge triangles. Have you visualized it now? 2 huge triangles. And then within 2 huge triangles, you draw 4 triangles, random triangles, 4 triangles inside the huge triangles. Have you did it? Okay, have you done it? Okay. Then for those small 4 triangles, you draw another 4 triangles. You repeat this pattern. And then you will end up with the mountings there on the other side. So that's the technique there. They just repeated apply 4 triangles on the top of the small triangles and repeatedly apply that you have this landscape. Okay? Okay, so I have 2 minutes left. So what I will show you is that for fractals, there are 2 types. So there's geometric fractals and algebraic fractals. Okay, I want you to remember, usually what I ask my students is to name the fractals. So I'll show them the fractals, they have to memorize it, and in their exam, it's like name that tune. So instead of name that tune, name the fractals. Okay, so with your sharp memory, I want you to remember as many fractals as you can. So this is the KOCH snowflakes, appeared in 1904 and developed by KOCH. Okay, this is Sierpinski triangle. Okay, named after Sierpinski, but actually not developed by. It's actually not developed by Sierpinski, but named after Sierpinski. And this is the CANTOR set by George Cantor. And then for algebraic fractals, the famous fractals under this are Mandelbrot set. Okay, so you see, the equation is very simple. It's actually z sub n is equivalent to z sub n minus 1 plus c, where your z and c's are complex number sets. In this example, they use z sub 0, the initial z, as the 0, the origin. Okay, and then they change the exponent a from 0 to 6. But for Mandelbrot set, it's actually z squared. Okay, and in every Mandelbrot set, if you zoom in, you will see Julia set. Okay, in the edge part of the Mandelbrot set, there is actually infinite numbers of Julia set. There is only one Mandelbrot set, but there are a lot of, or infinity numbers of Julia sets in one Mandelbrot set. Okay, then I will usually have 1 day of laboratory. I will show them how they can create their own fractals. You can use this software or this app from the web. You just need to log into internet. Okay, it's free. If you want some more complex, if you want the fractals to move and rotate, maybe you need to subscribe. But without subscription, this will work. So if you go into this page, you actually see this. Okay, you have a lot of basic fractals, geometric and algebraic fractals that you can manipulate. You can change the iteration, and then it will show you what's the base and motif it used, and it will even calculate the dimension for you. Okay, but for Mandelbrot set, for the initial version, you are not allowed to change anything. Okay, but for Julia set, you can change the complex number, and it will show you whether it's still in the Mandelbrot set or not. Okay, this is very interesting. You play on that. Then usually what I ask my students is I ask them to summarize it in terms of a table. Okay, I'll ask them to give me the name of the fractals, the illustration, and associated things they found in their daily life. Okay, or anything that they know looks similar to that illustration. Okay. Okay, I'm supposed to give a question. Then there's a prize, I think. And do I still have time? May prize? So, the answer for this question is actually one of the fractals I showed you earlier. Okay, what fractals that you can hold but actually has zero area. Anyone? Yes. KOCH snowflakes? No. The area is quite big for KOCH snowflake. Yes. Very good. Sierpinski triangle. So you keep deleting triangles, right? You keep deleting. If you delete infinitely, it will converge to 0. Okay, but you can still hold the Sierpinski triangle because it has edges, right? Next one. So can we give us your name later. Next one. Last one perhaps. Okay. Finite area with infinitely long perimeter. Yes? Please raise your hand so that you get the credit. Yes, ma'am. KOCH snowflake. So you keep pulling it, okay? It actually have infinite perimeter, but the area will also converge. Okay, the solution of the area will also converge. Okay, that's it. I'm actually about to show a video of the Frozen that will end my talk. But anyway, I will just end my talk with the statement, mathematics is beautiful. In any beautiful object, there is mathematics. Thank you. You have questions? Huh? You have questions? Perhaps you're hungry? You can also have lunch. No questions? Crystal clear as the snowflakes. Yes, ma'am. Question for that. Yes. Huh? Request? Yes, ma'am.
So unfortunately, I don't have also my iPad with all those. Can we request have a soft copy?
We will actually share it in a page that you can download all the slides. Ma'am, later please come forward to give us your name. Because you will have actually free registration next year, right? Next PPP. So, pag walang questions, okay, thank you.
Okay, at this point, we would like to award the Certificate of Appreciation to Dr. Angelyn. May we call on our chairperson, Dr. Salle.